Our first unit of study is on kinematics. Kinematics is the study of motion without any regard to its cause. It's basically a way to describe motion. Well, before we get into this unit on kinematics, I just want to take a moment and talk about inertia. So Galileo, there's a name you're probably familiar with. He's famous for an experiment in which he rolled a ball down two inclined planes facing one another. And he found that if the two inclines are equally steep, the ball rolls just as far up the second incline as it rolled down the first incline, and by doing so, rolls to the same height it was released from. So then he tried the experiment again and had the second incline not quite as steep as the first. So in this case, when the ball was released from rest, it rolled to the bottom, and it rolled a greater distance up the second ramp or along the second ramp than it did the first. But the thing that comes out the same is it returns to the same height. So he carried this experiment on and had it where the second ramp was almost flat, and found if the ball was released from this height, it would roll pretty far up or along the second incline, always reaching the same height. So this led to a thought experiment, and Galileo wondered, what if I roll the ball down one incline, and then the second incline is essentially not an incline, it's flat? Then, does the ball continue to have a desire to try to return to its initial height? Well, in doing so, it would end up rolling on forever and ever and not stopping. And this is how he came to this concept of inertia, which you've probably heard described before as an object's desire to stay at rest if it's already at rest, or the object's desire to keep moving if it's already moving. Inertia and mass are, they're not just related quantities, they're basically synonymous. Mass is what gives an object its inertia. The greater the number of kilograms that something measures to, the greater its desire to stay at rest if it's already at rest, or the greater its desire to stay in motion if it's already in motion. If a tennis ball was rolling at you at 10 miles per hour, you'd have no problem trying to stop it with your foot or bend down and catch it with your hand. If a bowling ball was rolling at you at the same speed, you'd be a little bit hesitant maybe to try to stop it with your foot or to reach down and grab it with your hand. And if a semi was coming at you at 10 miles per hour, the same speed as the tennis ball or the bowling ball, you would definitely get out of the way. They all have the same speed, but each of them has a different inertia because each one has a different mass. So there's really no distinction between mass and inertia. An object's amount of mass measured in kilograms is what determines how much it wants to continue moving once it already gets moving. So in future chapters, we'll maybe draw a diagram of this sort. We'll explain why the ball rolls down an incline by saying, well, there's a force that we can represent by this arrow of gravity that pulls straight down, and in combination with that force pulling straight down, the incline itself pushes perpendicular to the incline, sort of up and to the right. And the combination of these two forces ends up, if we use something known as the parallelogram method for adding two vector quantities together, we can make a parallelogram out of these vectors and find that the result is this green arrow pointing parallel to the incline. Now maybe you've seen that before if you've taken a previous physics course. If this is foreign to you and you're not sure exactly how I came up with this parallelogram approach, don't worry, we'll get to that in a chapter on forces and Newton's laws. For now, we're really not going to talk about why objects accelerate on a ramp and maintain constant velocity on level ground. We just want to come up with a method of explaining these two different types of motion. How can we describe accelerated motion versus motion with steady speed or constant velocity? So this concept that something will continue to move indefinitely, never coming to rest if it's already moving across level ground, might be a little bit foreign to you, right? Certainly if you were to get up to speed on your bicycle on level ground and then take your feet off the pedals and try to coast, you know that in time, eventually, you're going to slow down. But, of course, the reason for that is because there's a force of air resistance pushing back against, or there's a little bit of rolling friction between the wheels and the ground. But then again, those are forces, and we're not going to talk about a study of force until we get into Newton's laws. So if you could completely eliminate the air resistance or eliminate the friction, then an object would move a little more like what we see when we play air hockey. And that might be a better example of an object that once it gets moving, wants to continue moving at a steady speed. You can make your own air hockey table just using a piece of dry ice. If you have a flat tabletop, maybe a granite countertop or something like that, if you take a chunk of dry ice, maybe you order something really cold in the mail and it's shipped in dry ice, or you can go to the grocery store and ask in the meat department for dry ice, they'll sell it to you. If you get a hammer and maybe a screwdriver and chisel away at it, you can chip off a little piece of the dry ice. And if you take that little piece of dry ice and you put it on a flat tabletop, it outgasses, it sublimates, right? It goes from a solid to a gas without going through the liquid phase. And it doesn't just sublimate off the top surface, it does so off the bottom as well. And so it creates its own little cushion of air that it glides across. And if you just give it the slightest little flick in one direction, it'll drift in a straight line and really doesn't slow down like you do when you take your feet off the pedals on a bike, or like taking your feet off the gas pedal on your car or something like this. So the end result of this concept of inertia leads us to two types of motion that we'll study. One, if there's no force acting on an object. Actually, I'm going to insert a term here. I'm going to say, what if there's no net force? Maybe an object is being pushed to the right just as hard as it's being pushed to the left, or it's being pushed up just as hard as it's being pushed down. So it's not to say there are no forces acting on it at all, but the sum of all the forces balances out to zero overall force. In that case, well, here we'll use this symbol, right? That's a mathematical symbol for summing everything up. So if the sum of all forces is equal to zero, then the result is the acceleration is equal to zero. And zero acceleration means constant velocity. So we'll start with a study of objects that just move with constant velocity. I'll reference something known as the dirt equation. I guess we can leave the I out of dirt. The dirt equation is just a way of remembering that d equals rt. Distance equals rate times time. Excuse me. Actually, I don't like writing it like that. I'm going to say delta x instead of d for displacement, and I'm going to say v instead of r, right? Instead of saying rate, I'll say velocity, and then t for time. There we go. Displacement is equal to velocity multiplied by time. Okay, the second type of motion then obviously is, what if the sum of all forces doesn't equal zero? Well then, that's what it takes to overcome an object's inertia. When a force is impressed, the more mass an object has, the greater the amount of force it would take to get it to accelerate, or the less it would accelerate given a certain force. We can say that mathematically. There's a better way for me to repeat what I just verbally fumbled through, right? We said there's three quantities we need to be concerned with. How much force is applied, how hard do you push or pull something, how much inertia does that object have, but remember, there's no distinction between mass and inertia. So we'll just use the symbol m to represent that quantity. And then how much does the object accelerate as a result? We can just use the symbol a for acceleration. So here's three variables: force, mass, and acceleration, that are all related. And again, if you've taken a physics course before, you better know the equation that I'm hinting at, right? It's known as Newton's second law of motion, and it says the acceleration that an object experiences is directly proportional to the net force applied, yet inversely proportional to the amount of inertia that the object has. So what we really need is some sort of study that relates these quantities: acceleration, speed or velocity, how far something travels, and the time it spends traveling. This is really the emphasis of kinematics. It's a unit of study that doesn't really get into a discussion of the forces involved that make an object accelerate or change its velocity. Kinematics is just that study of motion that we use as a way of describing and relating the quantities that describe how fast, how far, or how long. So as we get into this study of kinematics, keep in mind this term inertia is synonymous with mass, and because of an object's inertia, when there's no force impressed at all on an object, it tends to move with a steady speed. And the first type of motion that we'll investigate is exactly that: objects that maintain a constant velocity. So that's all for this first introduction. Thanks for watching, and continue to watch the rest of the videos on this first unit known as kinematics.